I'm Yan Gao. I'm going to present our work, DeepTheft, Stealing DNN Mode Architectures Through Power Set Channel. This is a collaborative work with Fudan University, the University of Western Australia, Illinois Institute of Technology, and Nanjing University of Science and Technology. Machine learning as a service is quite common nowadays, where the clients can train their models on the cloud, as well as deploy their models on the cloud to provide inference services for profit. Typically, machine learning as a service are offered by a number of giant companies such as Amazon, Google, and Alibaba. We consider the model provider deploying their models in the cloud to provide inference services. In this example, a user can make an inference query by sending an image to the cloud. The deployed model conducts the inference and returns the result to the requested user. For example, the label of dog is returned to the user. However, the deployed model is under different threats, including adversary example attack, privacy inference attack, and model stealing attack. This work considers the model stealing attack, in particularly those attacks aim at accurately steal and the model architecture. The reason is that the model architecture is a key factor of the model performance, thus a valuable intellectual property for the model developer or the model provider. There are typical two approaches to design high-performance model architectures. The first is through manual design, such as the ResNet and DenseNet, which however requires substantial human intelligence. The second is through automatic design, such as through the neural architecture search, shortly the NES, which however requires extensive computing resources. Therefore, once the model architecture is exposed, it has a number of negative consequences. The first one is the IP infringement to the model developer or the provider. More severely, the model architecture is essentially a premise for many further adversary attacks. For example, the deep steal or steals model ways needs to have knowledge of the victim model architecture. Other attacks' performance is also highly dependent on the knowledge of the model architecture. Those attacks including membership inference attack, delivery construction, and backdoor attacks. There have been a number of works demonstrating the model stealing attack, which we summarize in this table. However, almost all of them require physical or proximate access to the victim machine that deploys the model. For example, to leverage the electromagnetic side channel, the attacker needs to put the sensor closely to the victim machine. This distance is within 30 meters. The cache telepathy is the only work that avoids the physical or proxy access to the victim machine. It uses cache as a side channel. However, its tagging accuracy is low. As for the deep steal, it leverages rowhammer as a side channel, but this work is not for model architecture stealing. It actually assumes that the model architecture is known by the attacker who steals the model weights instead. To this end, we ask the following research question. Is it feasible to leverage other side channels on general CPUs to accurately and steadily steal complex DNN architectures with legitimate system access? We then propose DeepTheft. DeepTheft is a learning-based framework that can accurately recover not only the model structure, for example, the number of layers and layer type, and layer-wise hyperparameters. In fact, DeepTheft can be incorporated by side channel information as long as such information is like a time series signal. Our attack has the weakest threat model since the attacker only needs black box access to the victim DNN model. Nonetheless, we assume that the attacker controlled process is coincided with the victim tenant in the same machine. In the cloud, a physical machine can be shared by multiple tenants. It is assumed the attacker and the victim tenant who deploys the model on the same physical machine. The attacker pretends to be a normal user, sends an inference request to the deployed model. The model executes the inference and returns the inference result. In this attack, the inference result does not matter to the attacker actually. What it matters is the side chain information measured and collected by the attacker during the model inference execution. We consider and evaluate the DeepTheft with two side channels that are power and frequency side channels respectively. The power information is accessed through the ripple interface. The frequency information is accessed through the DVFS interface. Both interfaces are provided by Intel and AMD CPU processors. The vulnerability of the repo has been disclosed by Platypus, published in 2021 Auckland. Repo full name is Running Average Power Limit. It's an interface for reporting accumulated energy consumption of various power domains supported by Intel and AMD processors. Heartbleed is a frequency-based side channel enabling remote attacks given an unprivileged user access. This vulnerability has been disclosed by Heartbleed in 2022. Usenix Security. Heartbleed is a frequency-based side channel enabling remote attacks given an unprivileged user access. It essentially exploits execution time difference caused by dynamic frequency scaling, a CPU feature which changes the processor's frequency to maintain power consumption and temperature constraints. Different AWS EC2 instances provide a balance of compute, memory, and networking resources, and can be used for a variety of diverse workloads. We have evaluated some of the AWS EC2 instances to see whether the access to repo is allowed. We found that some instances do allow it. The tested instances are listed in this table. As Intel says, they know that repo interfaces have a limited sampling rate, low sampling frequency, and low resolution, which makes most attacks using these methods actually difficult and time-consuming. This is true because we found that the sampling rate of the repo is only 1 kHz. Overall, to address the challenge, the DeepTheft uses a two-step divide and conquer strategy. The first step is layer segmentation. Given energy trace, it uses a meta model to segment the traces into different pieces. Each piece corresponds to one layer. The second step is to recover hyperparameters given a segmented layer. In this example, the model had 7 layers. The first step is segments the energy traces into 7 pieces. Different layer has different number of hyperparameters. Convolution layer had 7 hyperparameters, while maximum pooling layer and linear layer had 4 and 2 hyperparameters respectively. For some layers, they do not have any hyperparameters. For example, the ReLU and average pooling layer does not have any hyperparameters. Even for the layers with hyperparameters, not all of them need to be recovered through learning approach. For example, the padding size of the convolution layer can be deterministically determined once other hyperparameters are decided. Specifically, it can be derived once the kernel size and dilation are gained. In addition, some hyperparameters can be determined through domain knowledge. For example, the dilation is commonly said to be 1. The table here highlights those hyperparameters do require recovery. Convolution layer had 3 left, while maximum pooling and linear layers have 3 and 1 left to be recovered. After overview the DeepTheft, we can have a look at its design. Regardless of the offline or online files, the attacker has legitimate access to the repo to measure the CPU power consumption when the model executes the forward inference computation. During the offline files, given training data with annotated ground truth labels, a number of machine learning models, namely meta models, are trained. During the online files, given an unseen energy trace measured during the execution of the victim model inference, a meta model firstly segments this trace into different layers. Then for each hyperparameter, a corresponding meta model is used to recover its values. To this end, not only the model structure but also its hyperparameters are recovered. Among a number of meta models, the meta model for layer segmentation is very important because if the layer segmentation has something wrong, the second step of layer-dependent hyperparameter recovery will completely wrong. The layer segmentation faces 2 challenges. Firstly, the sampling rate is very low, only 1 kHz in our case. As a comparison, the sorter work has a sampling rate of 47 kHz. That is 47 times higher. Because of the low sampling rate, some layers have only a few sample points, especially for average pooling layer and linear layer. To address these challenges, we designed the meta model with a novel architecture, which is a hybrid of UNet and bidirectional LSTM. Here is the detailed design of some blocks. Here the UNet is good at capturing special features. The UNet is widely used in image segmentation. The bidirectional LSTM is good at capturing temporal features, which is commonly used for time series forecasting. Now we complete the metamodal architecture design, but have we solved the challenge yet? Not yet, actually. We also need to formulate optimization objectives to efficiently guard the metamodal training. Here, we designed two optimization objectives, or two loss functions. The first is namely sampling point independent loss. Given each sampling point, it is classified into a layer type. In this example, the first 2 points are classified into layer 1 or convolution layer, and the third point is classified into layer 2, and so on and so forth. Note that this loss can only capture special information. Obviously, the third point is wrongly classified. Therefore, we designed the other loss function to incorporate special features or contextual information. This is a cross-sampling point loss. It has two merits. Firstly, given special context, it can correct some misclassified points. For example, the third point now is corrected into its correct type 1. Secondly, it helps to choose the right layer path given the special characteristics. Here, suppose we have a model with 3 layers. There are different combinations of 3 of these layers. We name each combination as a path. Path 1 has a linear layer followed by ReLU layer, then linear layer. Path 2 has 2 consecutive linear layers followed by a ReLU layer. The cross-sampling point loss enforces the right layer path is most likely chosen. Here the path 1 is chosen. After resolve challenges of the first step of layer segmentation, we have further resolved some challenges related to hyperlayer recovery. Overall, we address them through a layer-wide strategy and incorporate domain knowledge to reduce the number of hyperparameters that are essentially required to be recovered. Because some hyperparameter can be determined by domain knowledge or deterministically derived once other hyperparameters are known. More details can be found in our paper. Now we present some key results. Because there is no public dataset related to recovery model architectures through sidechain information, therefore we have collected a large-scale dataset and released it to facilitate the community. The dataset considers 11,152 different model architectures, including those randomly generated and from standard models such as AlexNet, VGG, and ResNet under different configurations. The network depth ranged from 2 to 152. The deepest network is ResNet 152. We further consider 5 input sizes that are the image size accepted by the underlying model. Here, 331 means the input size is 331 times 331 times 3, which is a color image. In total, we have collected 55,760 energy traces. The number is 11,150 times 5. Among them, 5,760 energy traces are reserved as test dataset. The dataset size is about 20 gigabytes. To measure the segmentation accuracy, we use 2 metrics. The metric 1 is LDA. It is the similarity between a predicted structure and a ground truth structure. The metric 2 is segmentation accuracy, or SA, is the percentage of sampling points that are correctly predicted into their ground truth layer types. Here we can see the DeepTheft exhibits super accuracy for layer segmentation. Both SA and LDA are close to 100%. For the layer-wise hyperparameter recovery, the accuracy is measured by precision recall as well as F1. We can see the DeepTheft performance is also very high. Each metric achieves more than 99.5%. Besides evaluating the power side channel information, we have evaluated the DeepTheft performance when another side channel information, that is the frequency, is used. The bottom subfigure shows the frequency trace, which we can visually see that the trace is dependent on layer types and hyperparameters. By applying our DeepTheft, that is a general learning framework, we obtain the LDA and SA of both about 99%, which is similar to that gained from the power trace. We have performed other observation studies and compared our work with the sort work, which details can be found in our paper. Thank you.